So good evening to all of you. We are just started our session 3, day 2. So our expert is Dr. Dhiman Das, and we introduced him already. So we are not waste today's time. So sir, you can start your session.
Thank you, Devabrata. Okay,
Thank you,
let's start.
sir.
Okay. So, good evening, all of you. So, today I'm going to discuss a detailed sub-switching mechanism of LLC converter and dual active bridge converter. So, this is a topology of LLC converter that we discussed yesterday. Here is input voltage and one active bridge, and this can be full bridge, can be half bridge also, depend upon your voltage level and power level. So now this output of the bridge is fed through an LC tank, and for isolation, this is an isolation transformer. So at the secondary side of the transformer, the injected current is uh, flow at the secondary side. The voltage is induced and the secondary. Yeah, voltage is induced at the secondary, and the current is reflected at the secondary side. And the secondary side, you can either place a diode rectification, center tap, or full bridge diode rectification, or you can use synchronous rectification for high current application. Now that this resonant current you can dump to a capacitor to have a clean voltage waveform. So you can from the capacitor you can connect the load. You can take the output current as a DC current. So this is widely used in telecom power supply. As we discussed yesterday, also primary side having GVS, secondary side having GCS. But the problem is that control is difficult because of the gain characteristics of the uh, resonant network. So similarly, this can be the primary side can be replaced with half bridge cell, but when you replace that, your voltage will be no longer plus minus swing. It is plus and zero swing. So when it become plus to zero swing, your gain will be directly half of the previous one, half of the full bridge. So this network have giving the half bridge gain. But now in this case, your current is pulsating in nature. That means in one switching cycle, you can have a positive current, but in another next switching cycle, you will get zero current, again plus current, positive swing. So if you connect want to filter this current at the input side, you want DC current, but this pulsating current, if you want to filter it, then you need a big capacitor so that this ripple will get absorbed by the input capacitor. To avoid that, that is called asymmetric half bridge LLC. Now to avoid that, you can connect a two splitted capacitor and connect this switching network towards the midpoint of the capacitor. Then you can have a full swing across each cycle. The half swing at each cycle. full swing you can get across the tank, but at the input side you can get half swing in each cycle. There is no blanking period. So for that, the input capacitance, the requirement of input capacitor or input filter will reduce, because your current is no longer pulsating in nature. This is an rectified version of the sinusoid. The secondary side, you can either do center tap, or you can either go for this full bridge arrangement. The secondary side is not a problem at all. So now when you do the modeling, so your half bridge can be modeled as a switching function, or your full bridge also can be modeled as switching function. So total switching network you can replace with the switching function S of t, where S of t swing or vary between 0 and 1 in case of half bridge, and plus minus 1, actually plus minus 1 and 0 in case of full bridge configuration. Now when you mathematically when you multiply that switching function with the input voltage, you can get a plus V swing 0 and minus V swing across the bridge. Now that bridge voltage, when you pass through an LC network, you can with this pulsating voltage, when you excite a LC network, a resonating current will appear and across the network. Now across, when it is positive, the positive half cycle of the resonating current will flow through the network, and when it is negative or 0, the negative current will flow through the network. So the network gain, there is only if you see the simplified version of this topology, this converter, then there is source and this tank and only load. There is no other component. So this is the source, which is a pulsating voltage. Now when it is passed through the network, is depending on the gain of the network, the output voltage will vary. You see, there is no other component, so it is acting like an potential divider kind of arrangement. Now this tank characteristic is shown here. For higher frequency you can have attenuation, but this attenuation is depend on how what the attenuation and the gain characteristics is depend on the load, which is also called a Q factor. Now when load change, your curve is also change. Your all resonant curve keep on changing and changing. But if you notice one thing, at the resonant point you can have the regulation, but above the resonant point you will lose the regulation. That is why the controlling this converter is quite difficult. Now when light load condition, when the Q is very low, very low Q, you will see the curve is providing some boost action. Means you can achieve more gain compared to the excited voltage. That is because of the resonant phenomena, that you can have the boost action. But at the boost action at low frequency side, there is one possibility that you can cross the other region, which is capacitive region of the network. When you cross the capacitive region, then you will lose the GVS. Then when you lose the GVS, your switching loss will going to increase. But will you can achieve the GCS, but you with the GCS you cannot achieve, you cannot gain the reduction in switching loss. Your GCS does not help in anything. it can help in the EMI performance, but you cannot gain other than the EMI behavior. You cannot gain the uh, reduction in switching loss. So next, I will show you how do you identify which area of the curve it is operating. In the analytical aspect, you can see this is the curve, but in reality, you cannot. It is very difficult to predict that which area it is operating. Now, how do you identify which area it is operating? I'm going to show you. Okay, let's uh, before analyzing the mathematical analysis or any kind of experimental analysis, you must understand how what is the switching sequence and what is the soft switching mechanism or switching mechanism of the converter. This is very quite this is very useful to understand, but it's a quite complicated and quite difficult to understand at certain region. So let's start with a half bridge cell so that you can understand it very easily. So at half bridge cell, you can see there is two switch. One is top switch, one is bottom switch, and at the middle of the node, this is the voltage of the bridge. So at the top node, the positive voltage, and the bottom node, the voltage is zero. This is a battery or a power source, whatever you say. So that source is connected to the this hub bridge, and the middle of the hub bridge is either 0 or 1. So when top switch is connected turned on, S1 is on, this node is connected to the positive supply of the or the positive node. Then your voltage across this node with respect to the ground is plus. Now when top switch is off and S2 is on, then potential at this node is 0. So in this way, if you turn on the switch S1 50% and complement the uh, pulse, and to turn on the S2 bottom switch, it's the same 50% duty cycle. So when you do this 50-50 duty cycle, complementary drive these two switch, then you can get a 0 to plus and plus to 0 swing across this node. Now when you, okay, let's start with the switching sequence. Okay, so between plus and between these two transition, when top switch is off and bottom switch is on, and bottom switch is on, top switch is off, bottom switch is off and top switch is on. There is two transition. Between these two transition, one date time is inserted. This date time is how this date time is, how much date time you want to put. What is the optimum value of date time, that we will show. Okay, so let's start with first switching sequence when S1 is on. So when S1 is on, this uh, voltage across the switch is 0. Voltage across the S1 is 0 because it's turned on, and voltage across uh, the S2, voltage appear across the S2. One node is ground, another node is plus because it is on. So here, so the, okay, when you see the switch, when you see the switch, when we read this, if you do it in practical switch, a power electronic switch or MOSFET is combination of three elements. One is channel or the MOSFET, another is a back diode or body diode or anti-parallel diode, whatever you say. Another is the output capacitance, that is COSS. So these are the three element, basic three element you can consider for the analysis of the resonant or any kind of zero voltage switching action. So when S1 is on, so voltage across the S1 is 0. So the capacitor across this top switch CS1 is also 0. That means that is discharge. And opposite switch uh, is off. So voltage appear across this switch is V, and this capacitor uh, at the switch along across the switch is charged to value of V. Now in this scenario, a current will try to resonating current try to flow through the load and as well as through the magnetizing inductance or magnetizing inductance of the transformer. So there is two component, one is magnetizing component, another is load component. So now during turn on you can see there is one cycle. So this is the tank current, green one, and this magenta one is the source current or the switching current flowing through the switch. Now you can see the current start from 0 and try to make a half sinusoid. Then I turn off the switch. If I make if I turn on the switch for longer period, that means I am reducing the frequency. Then you can observe this sinusoid will get completed. Now before that is capacitive, that means we are going to capacitive region. Now you can see before completing the sinusoid, I'm cutting the sinusoid. That means I am operating at high frequency. I am going above the resonating frequency. That is why it become cutted. Now when I turn off the switch, so this switch is off. This switch is also off. That is called dead time. Now during dead time, what is happening? So during dead time, when both switches are 0, now the top capacitor is initially it was discharged. Now it is going to charge through the source current. That is why you can see there is a slope across the source current. It is not immediately 0. You can see it start here. I cut, I end up the gate pulse here, but still a little amount of source current is flowing. So this source current is try to flow to the network and try to charge the capacitor. Now when it charges this top capacitor, so voltage across this across this switching across the switch is going to increase, and as similarly the bottom capacitor was charged, now it is going to discharge through this network because this network is connected to across the across this node. So this capacitor, the bottom capacitor, going to discharge through this resonating network as well as this magnetizing current. So voltage across this switch is going to drop and voltage across this switch going to increase. That means this capacitor is charging and bottom capacitor is discharging. Now when it is fully charged, the top capacitor is fully charged. Now when capacitor is fully charged, it behave like an open circuit. Now you can, for simplicity, you can assume the source is disconnected from this node as it is fully charged. Now when it is charged, the top capacitor is charged, the bottom capacitor is fully discharged. Now, as the bottom capacitor is discharged, so there is only one other path to circulate the current, that is the body diode. Now this magnetizing current turn on the body diode. Now you can see uh, this current, this is the switching current of the bottom switch. You see there, here it turn on the, this is the negative current, because the current is negative because uh, you see the current is entering to the device. When we assume that current is entering to the device, then as per the sign convention of current, we can see this is the negative current. Now this negative current try to flow through the across the body diode and try to charge this network, try to circulate along this network. Now when it happens, so this negative current going to 0, and from 0 it try to go to positive. So now when during that time when it from negative to 0, that is the, that much duration you have in your hand, that when the current is going negative to 0. So during this period, that is the optimal get dead time. Now when it from 0 onward, from 0 to positive, when it going to circulate, then your body out the path, along this path is the voltage drop across the body diode multiplied by your current. That is the power dissipation happen across this path. So immediately when it touches the 0, you need to turn on the switch, this switch. Then it will no longer flow through the body diode, it will flow through your channel of the switch. So that is the optimum amount of gate time you can insert between this uh, network. So now when body diode current start 0 to positive, then you turn on the switch, the bottom switch. Is there any question up to this? You may please ask. Then I will go to the top mechanism of top switch. No questions so far? Okay. So now you turn on the S2. So now when you turn on the S2, you can see the current across this S2 is 0. Already body diode is conducting. That means voltage across the switch is 0. Now you can see here is 0. The current is 0. That means you are doing, there is no current stress and voltage stress across the switch. That is called soft switching mechanism. Now when you turn on the bottom switch, your okay, so now CS the top capacitor is fully charged and the bottom capacitor is fully discharged. So now when you turn on the bottom switch, this negative half cycle of the resonant start to appear. So the LM going in negative direction. LM is a triangular wave or triangular shape. So it's going to negative direction, and the CR or the capacitive capacitive voltage going to negative, and it try to discharge, the capacitive voltage try to discharge across the network. That is the negative side, negative sequence of the resonance. Now similarly, after a certain time, this time, you see this current is negative in the direction, the tank current, But during negative direction of the tank current, it is not at all extracting any current from the source. That is why source current is completely zero up to this. Okay, now you can see there is a negative version of source current. That means some current is pushing towards the source, which is a reactive current, because the when you push the current back to the source, that is negative in direction, that is called reactive current. Now we will understand what is the effect going on. So now the capacitor, bottom capacitor is discharged and top capacitor is fully charged. Now when both switch is off, then with this resonating network, the top capacitor try to discharge because negative current is flowing. Since that is the negative version or the negative half cycle of the resonance, and it is charged to positive value of V, that means it is going to discharge in negative direction or with a negative current. So the top capacitor is going to discharge towards the tank, or through the tank current towards the input, and the bottom capacitor is going to charge. So you can see there is only one path, one circulating path. So that is the tank current. So this tank current try to charge this top capacitor, and when this capacitor is fully charged, the bottom capacitor is fully discharged now. Now when the top capacitor is charged through this tank current, then fully charged, then the body diode start to conduct. Now uh, 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 sorry, the top capacitor is fully discharged, then body diode start to conduct. Now when the body diode start to conduct, the current is start to flow towards the source. That is why you can see a negative current across the towards the source current at the source current. This is the bridge voltage. You can see the bridge voltage is swing from 0 to uh, plus value, but here you can see there is negative current, but your gate pulse is here. You can see your gate pulse is here where negative current touches the 0. So from here to here you have that adequate dead time. You can tune your network and you can have this dead time. So in this way you can achieve a full zero stress across the switch. So there is 3 mode of operation of this converter. One is buck operation, another is resonant, and is boost. So in buck operation, you can see if you can see the current profile is negative when you start the switching. That means this is a buck operation. And also if you see the tank current, you see it is not completely, the sine wave is not completed. Before that I cut the sine wave by switching action. In resonance mode, you can see this is full swing across the tank current, the full resonant current swing. So at resonant mode, gain is 1. That means whatever the voltage appear across the resonant tank, it is fully um, transferred to the load. Your impedance is the 0. That means your capacitive impedance and inductive impedance cancel each other, and you will get the fully reflection of the bridge voltage. But you can see there is also still a negative current, that is because of the LM. Because LM, I am feeding back the current from the uh, load. Uh, yes. So this is also GVS region. This is also GVS region. But when I decrease the frequency, or I lower the frequency, you can see the sinusoid is already completed. You can see the sine is already half cycle of the sine is already completed. Now I allow the switch to operate more time, for more time. Now what will happen? It goes into the capacitive region. At the capacitive region, if you see the source current, you can see when you turn on the switch, the voltage is not at all zero. There is some voltage remaining, or the current is not zero, not negative here. So when you turn off the switch, you can see the negative current here. That is why the voltage trace across this switch here is more. You can see the ringing and all the this is no longer soft switching. Your switching may blow up at this condition. If you don't your parasitic element can destroy your switch because of the ringing here. Your ringing is not damped here, but earlier with this mechanism, we are damping the resonant, we are damping the parasitic, we are using the parasitic element to charge the capacitor, or we can say we are using the parasitic energy to charge up the capacitor and damp this element, this parasitic current towards the parasitic body capacitance. That means we are not adding any extra component. We are using that parasitic component of the circuit. So at boost mode, you can get higher gain compared to input voltage, but in buck mode also you can have lower gain compared to input voltage. This picture I showed yesterday also. You can see when switching in the simulation also, you can observe the same thing here. So this is when voltage uh, is swing. You can see there is the voltage across the bridge does not change abruptly from 0 to 300 volt. It is following some uh, following a parabolic shape. That is because of the body capacitance of the switch. So body capacitance try to charge slowly by that current, but LM current or magnetizing current. And you can see there is still the tank current is still negative. And see, you can see uh, this is the negative portion of the current that I show in the simulation. See, this is the negative portion of the current, and this is the resonant current is flowing. You can see the resonant current touches the zero at this transition, but your tank current does not touch zero. It touch zero here. And this is the capacitor voltage. You can see there is the positive half cycle and the negative half cycle of the capacitor voltage, and also positive half cycle and negative half cycle of the resonant current. Okay. Now at no load condition, you can see there is a magnetizing current flowing through the network, which is triangular in nature. When the voltage across the network is zero, it is magnetizing current is discharging, and when it is on or high, the magnetizing current is charging positively. You can see there all the parasitics. It should be ideally triangular in nature, but due to the parasitics of the actual circuit, it is there is high frequency component is overlap on the this current. Okay. Now we are going to discuss another topology or another popular topology, which is dual active bridge. So in LLC, we see this kind of one active bridge, but it that active bridge exciting one LC network, and that secondary side and the current is generating the resonant current generating because of the excitation, and that current is transferring the secondary with the transformer and dump to the secondary side capacitor. Now uh, at the at the secondary side, uh, in the uh, in the LLC converter, that is either a diode bridge or a synchronous rectification. But here, in case of dual active bridge, we are exciting the transformer, both edge of the both winding of the transformer with a uh, one with two active bridges. One active bridge at primary side, another active bridge at the secondary or low voltage side. One is high voltage side, one other is low voltage side. So here, if you say primary, secondary, then it is confusing because both side is excited together. So both side you can say primary. So that is why it is better to say high voltage side and low voltage side. So this is galvanically isolated, and bidirectional power can be transferred between two bars, which is high voltage and low voltage bars. So with a common converter or common interface, and you can operate this converter in very wide range. In LLC converter, you cannot operate the LLC converter in very wide range. Okay. Now let's see the operation briefly. So the primary side of the bridge is full bridge. That means you can have a pulsating plus and minus. Now, when at the secondary, at the low voltage side also, you can have a plus and minus waveform. Now, when you reflect this uh, plus and minus waveform, that means a pulsating waveform or a square wave waveform to the secondary or high voltage side, it will be just reflected by, it will just multiplied by n times, because this is n is to 1 transformer. Now you can see when if you shift now if you shift the secondary side pulse with angle phi, so you can see there is an instantaneous voltage difference across the inductor L. Now at mode 1, you see with this difference the inductor current try to shoot up. Now after that, there is no such voltage difference, so inductor current will no longer rise, and the inductor current try to discharge. So similar action at the mode 3, there is the high voltage side bridge is negative and low voltage side bridge is positive. That means if you calculate the polarity of the current with respect to the high voltage side, so it is going towards negative. Now here at mode 4, you can see the voltage across the voltage appear across the inductor is 0. That means the current is trying to discharge. In this way, a bipolar current is generated across the inductor. Now that current is flowing through the secondary side as well because of the transformer action, and that current is dumped to the capacitor and to flow through the low voltage side. That means the current amount of current is influenced by the phase shift angle phi. If you increase the phi, you can see the slope of the current try to go rise further. If you shift the angle phi up here, then your slope will be here. Similarly, if you in the negative side as well. So the power is transferring from in leading bridge to lagging bridge. Here, high voltage side bridge, I am assuming leading bridge. You can do the opposite way as well. That is the beauty of the dual active bridge. In LLC converter, you have seen that this current or the is a sinusoid in nature, but here you can see it is trapezoidal in nature. It's no longer a sinusoid, it's trapezoidal in nature. Okay, now if you want to design any controller of dual active bridge, how do you do that? Because there is 8 switches now. How do you control the 8 switches? So there is you can for simplicity, there is one high voltage bridge and one low voltage bridge. So switch is S1 to S4 at the high voltage and Q1 to Q4 you can assume at the low voltage bridge. Now you can measure the voltage and current, and eventually you are trying to control the amount of power transfer from leading bridge to lagging bridge. So when you do so, you need to take a voltage sample and current sample and multiply by the and multiply those two signal and to get the power. Now since it is a bidirectional power transfer, so this power can be positive as well as negative. When you transfer from HV to LV, you may assume that power is positive. Now when you do the reverse transfer of power from LV to HV, then the sign of the power is going to change in the opposite direction. That means PM is going to plus and minus, but your PI controller does not uh, take this bipolar action. So for that I need an absolute value amplifier. If I pass through the absolute value amplifier, this is just an, you can assume a rectifier, but not a diode bridge rectifier. In diode bridge rectifier, there is certain voltage drop across the diode that you cannot avoid, and these are low level signal in the range of 0 to 3.3 volt or 3 volt. So if your diode drop is around 0.7 volt, then 1.5 volt is just gone from your measurement. So you can have a erroneous result or erroneous control, or that control is clipped. For that I need an absolute value amplifier. So this is an active amplifier or active rectification using op amp. So here you can also operate at high frequency. So here you can see the you if you pass through the PM at the absolute value amplifier, you can have mod of PM. That means irrespective of the uh, magnitude, you can just have the only the sampled value, only the value irrespective of the magnitude. Now if you the reference signal that absolute value, then you can have the error amplifier, and that error signal if you pass through a compensator, the total thing is error amplifier. Then you can have a control voltage. Now that control voltage, when you pass through a phase modulator, phase and compare with a triangular signal, then you can have a sorry, compare with the ramp or triangular, then you can have a phase shift. That phase shift is if you translate into gate signal, and when this gate signal, if you pass through a switching multiplexer, then you, with that gate signal, you can either trigger the S1 to S4 and Q1 to Q4. Now when you change the direction, the S1 become Q1 and Q1 become S1. When you do so, then your lagging bridge become leading bridge become lagging bridge. If you, it's just like a mirror image by changing the direction input. So through the switching marks, you can do that. Now when you do so, your power flow will be just opposite in reverse direction. So similarly, you can replace the switching network with the switching function S of t, when where S of t is +1 for half cycle and -1 for another next cycle, next half cycle. Through a full cycle period of ts by 2 is +1, and from ts by 2 to ts is -1. Now if you can reduce the whole circuit, instead of switch, you can just replace the whole circuit with switching function. So at the primary side is S of t, at the secondary side is Q of t. And that is the interface inductor between the two. This IL is actually controlling the amount of power flow. Now you can see there is only two nonlinear block, S of t and Q of t. Rest of the thing is linear circuit element. So if you do the first FFT and first harmonic approximation, then you can just have this. You can linearize this switching network using first order approximation and first order harmonic and DC component. So if you do so, then you can come up with this equation. So now you are linearizing the switching function with the real and imaginary and DC term, which is first order harmonic term. So when you do so, you can have a sine and cos because of real and imaginary and a DC value. Now if you do the mathematical derivation, you can get the state matrix of the control of the converter. So where you can assume this voltage across this capacitor is a state, and the current through passing through the inductor is also another state. And your output is output matrix is I naught, which is the output current. So from there you can calculate the control to output transfer function. Your output is current and control variable is phi. Then your control function you can calculate from here, and you can plot the control to output transfer function through MATLAB or any kind of mathematical tool, and you can have this border diagram here. So this is the uncompensated system or raw plant. Now you need to characterize the you need to verify this equation, whether your assumption or whether your calculation is right or wrong. Already you have done the first order approximation, so you need to verify approximation is matching with the actual plant or not. So in order to do that, you are just break. This is most popular way to validate any kind of plant or any kind of converter. You just break this loop, and at the control voltage you can inject different frequency of the control voltage. You can superimpose this control different frequency on this control voltage. So when you do so at different frequency, you will get a different gain input to output to input, and different frequency. You can see you can this dot this dot you can, so you can see this, you can analyze the magnitude and phase as well. So when you get the result, you can just compare in the existing plot. You can just plot over this existing plot using MATLAB, and so in this way you can verify whether your modeling is correct or no. Now from the uncompensated system, uh, uh, we can see that I can have I can have a 20-degree boost from this gain margin and phase margin theory. So I can still I can get 18.5 dB of gain margin and phase margin of 90 degree. So I can still have some phase boost of 20 degree. And these are the control. If you This is the controller circuit. If you try to analyze, try to do the pole, analyze the pole and zero of this circuit, you can have these equations, this pole equation and zero equation in terms of the resistance and capacitor. So now if you do the Bode plot of this thing and uh, do the phase and gain calculation, then you need what is the pole frequency and what is the zero frequency, then you can end up with this value. These are the practical value. This value you need to put in this controller, then you can get this kind of gain margin and phase margin. Now when you do the when you plug this value in this uh, this error amplifier or the compensator, so this is the Bode plot of the compensated system. Here you can say how much phase margin and gain margin you get. Or from this 0 dB line, how much gain margin you have, and from the 180-degree line, how much phase margin you can get. These are the basic theory of compensator design. And this is the setup of the dual active bridge. Here you can see this is the gate driver. These are the gate driver, and this is the bridge at high voltage side, and this is the at low voltage side. You can see the waveform. There is a phase shift between these two, and the current is flowing. You see the shape of the current. These are the gate driver connected uh, to the setup, and these are the waveform how it is controlling. So this is the ramp signal, and this is the control signal. So at the timestamp when these two value matches, it create a phase shift of phi. So if you increase the control signal here, then the phi will be here. That means more amount of current is injected towards the from one side to another side. Now when you when you oscillate this control voltage along this operating point, which is called the perturbation. If you perturb this control signal uh, with a certain amount of frequency, then your phi is also get perturbed, or it's going to oscillate with that same frequency, because this point is moving slowly. When you do so, you know the phase and amplitude of this perturbation. Now you can collect the output current, and you can analyze what is the phase difference and what is the amplitude deviation happen between steady state and perturbed state. In this way, you can model the actual plant, or you can verify the analytical and model with the actual uh, plant. You can see uh, due to this phase shift, this amount of current is flowing from one side to another side. So you can see when I change the direction input, this is leading bridge to lagging bridge, and you can see this, the blue, this color, magenta color, sorry, cyan color is now leading, this blue color is lagging now. That is why power is transferring in opposite direction. This is high voltage bridge and this is the low voltage bridge waveform. Okay, now if you see the output current, this is a 0, that means no current is flowing. When I change the direction input, so it is flowing from minus to plus. You see, one direction to another direction, and in vice versa, so from positive to negative. Okay, that's all from my side. If you have any question, you may please ask.
Dear participants, if you have any queries or question, you can unmute yourself and ask the question, or you can write also in the chat box.
Good evening, sir.
Yeah, good evening.
Sir, while working with the switches, suppose I'm getting a switch. I want to operate that with 100 kilohertz. So I'm purchasing the switch and I'm operating it at 100 kilohertz. Is there any requirement that we need to add a body diode for that?
I did not get your question. What do you
No,
say?
suppose I want to operate the switch at 100 kilohertz.
Hmm?
And to do that one, do I need to add a separate body diode, or the inbuilt body diode in the switch is sufficient?
What kind of converter you want to use?
DAB, sir.
No, in DAB, the body intrinsic body diode is sufficient.
Oh, that is sufficient.
Mhm.
Okay. It depends on different converters, sir.
Actually, generally in hard switch converter like full bridge, nowadays body diode is very fast. In old days, they connect external diode because this body diode was not that much fast. But in soft switch converter, that does not matter at all. You can
Okay.
you may see that how much time you have to control the body diode current in LLC converter. So in every soft switch converter is almost same.
Okay, sir. Okay.
Which I am using PSIM. PSIM is very good software for steady state analysis. So you can use PSIM.
There is a question written in chat box also, sir. Which topology can be used for implementation of a 30-watt dual and triple output power supply, which input voltage is 50 voltage and output voltage is plus minus 15 voltage using ZVA or ZCS?
You can directly use LLC converter. LLC converter is very much useful for this GPS GCS kind of thing.
So any other question from participant? You can unmute yourself and ask the question.
Sir, while deciding the dead time, uh, we need to do the simulation first, and from that we are estimating or any standard dead time values we can use.
Standard?
The dead time for the switch.
No, no, there is no standard dead time. It is completely depend on your plant. How are you how you are choosing the inductor and all these things. I showed you
Okay.
how to
Yeah,
how
yeah, and
to
yeah, yeah, I understood that. But do I
mm.
need to do any simulation, or in real time we can
In
use this?
simulation you can have a idea, but if you want to fine tune it, you need to do it in bench. You cannot fine tune in simulation software because this parasitics is very hard to model in PSIM.
Okay, sir.
Mm.
Thank you, sir.
From PSIM you can if you plug in the inductance and capacitance
Okay.
value, you can have an idea how much data time is required. Around
Okay,
that you
sir.
can optimize.
Okay, okay, okay. Thank you, sir.
Mm. Mm.
Sir, another question is written in chat box from Mr. Satish. Can we get better THD while using DAB than conventional buck boost converter?
What do you mean by getting better THD? This is a DC to DC system, so why I don't catch your question. In DC to DC system, there is no THD.
Yes, sir. Because in case of AC, we determine the THD.
THD, yes.
Mm. But though the DAB is DC to DC system,
Every LLC converter is also DC to DC system.
Mm.
When inverter is those kind of modulation, you should bother about THD. Those space vector modulation and all these things. In inverter modulation, actually.
sir, I have a question. So, with the help of DAB converter or DAB converter, we can increase the charging rate. That means we can decrease the charging time also with the help of DAB converter.
Uh, another one more time, please. I did not.
So, with the help of DAB converter, we can increase the charging rate. Uh, in conventional EV system, the charging time taken near about 8 hours to 12 hours.
No, no.
So
Your
with the
charging rate is depend on the battery profile of your battery. Actually, battery profile, not the converter. The converter is just transferring the power. Now, what you will do with that power, that depend on your load or your application. In any converter, you can get a full high current thing. It is not that DAB is special for high current, low time. Not like that.
okay, yes.
Mm. You can get better high current with LLC converter or any other converter also.
Okay, sir.
Now to extract the high current, DAB has some advantage, but it is not related to battery charging profile.
No, we can do that with other technology also.
Any kind of converter you can do, but in DAB there is some advantage that it can handle easily high current. This current profile is trapezoidal in nature, all these things, but nothing is related to battery profile.
Oh. So any other question from participant? I think, sir, there is no question from audience. So thank you,
Okay.
sir.
Yeah.
Thank you for your valuable presentation.
Yes. If there is no other question, then I can leave the meeting.
Okay. Thank you, sir.
Okay. Have a good day, and I always encourage all of you to do experiment with the power converter. Otherwise, it is uh, very difficult to understand the power electronics without hands-on experience. Um, so, any kind of help, uh, I can help. Any kind of help you require, always welcome. But do the experiments for sake of your learning. Otherwise, you cannot feel the power electronics. You cannot feel the power electronics by reading the book, and also try to simulate. With simulation, you can have an idea, but when you do the practical thing, you will feel that simulation and mathematics and the theory on the book all are completely different. They are linked to each other, but they are different in different practice. So I always encourage everybody to do the experiment. Without experiment, power electronics is nothing.
That means, sir, in simulation, the output is quite, say, high efficiency we get, but when we are doing that practical, it is quite difficult to get that point.
Not only efficiency, your all the parasitic inductance drop and all these things come into picture. Now, when you do the experiment, then you will feel the confidence that how to make your circuit more ideal to from practical to ideal. These are the skill of a power electronics engineer. That confidence you will get when you do the experiment.
Okay, sir.
Mm. Because in book or any paper or any kind of literature, we are just draw the MOSFET, but in MOSFET there are different phenomena going on when current is flowing. All those things we ignored in the literature or in the simulation.
Sir,
So
another thing I learned quite previous, that with the help of power electronics device, whenever we actually use power electronics device, it generates the harmonics, and we can eliminate the harmonics with the help of again power electronics device. Is it so,
mm,
sir?
active filter you are saying,
That means
those are active filter, right?
uh, that means with the help of power electronics, it inject the harmonics to the system, and we eliminate that harmonics also with the help of power electronics device.
Yes, if you inject the counter harmonics, that is called selective harmonic elimination method. When you, this is very old technique in any kind of uh, power quality book you can see, or any kind of power quality paper. The harmonics you cannot eliminate. You cannot. Uh, you cannot eliminate from your system. Whenever there is a switching from 0 to 1 in square wave, there should be a harmonics. There is always a high order harmonics, because if you do the FFT of 0 to 1 means a square wave, you can see there is third order, fifth order, seventh order harmonics. Now if your harmonics power or any or your harmonic, the strength of your harmonics is getting high and high, uh, then what happen is that you need to inject the counter harmonics in opposite direction of the harmonics. That is the power quality problem.
Okay, sir.
Hmm.
Any other question from participants? Okay, sir. Thank
Sir,
you.
which
Oh,
software you have
there is
used for the simulation purpose?
Uh, I am using PSIM, but you can
eSIM.
use, yes, you can use any kind of software, but every software, but you need to understand the logic of the software actually.
Yes, sir.
How the software is working. This software is nothing but a mathematical tool. I can show you if I share my. Can you show my screen? Oh, okay.
yes, sir.
Yes, see, this is the PSIM software. I am. This is very old version during my PhD days. Still, I am using this thing, so you can see everything. This is the resonating. Now, if I change it to runtime, you can see the output voltage also. Now, if I decrease the frequency, you see the output voltage is increasing. Also, you can see it is transferring from one region to another. You can see. You can see this is transferring from. Also, you can adjust the date time here. Yes, you can adjust the date time. You can play with everything, but you need to understand how software is working. You can see. See, this is going to capacitive region. See, voltage is also boosting. Ideally, it should be 50 volt, but see, this is a half bridge circuit that we discussed. 100 volt, it should be 50 volt, but instead of 50, you can see the boosting happening. 53.6. This is quite convenient software. In my company, I also use this PSIM. You can check the gate pulses as well, how your gate pulse looks like, how much dead time you, if you change the dead time here, you can see with respect to pulse, you see the dead time is increasing. Now, how this dead time is affecting your thing, you can see here. You see there is too much freewheeling here. Anything?
So, any other question from participants?
Actually, this PCM is more to realistic hardware. Means the oscilloscope and all these components are there, and it is very much useful to implement the control as well. That is why in industry PCM is used. Okay, so
Okay, okay, sir. I think there is no question now.
hmm, okay. So good night, all of you.
Good night.
I
You all.
hope you learn something from this session, and it will be pleasure if you learn something and if you implement those things in your life, in your research or anything.
Okay, thank you, sir, and good
Okay.
night.
Thank you, sir.
Good night, sir. Wow.
Thank you.
Thank you, all of you. Bye bye.